Okay, so it's now 3 o'clock, and I guess we're very pleased to have Professor Paul Steinhardt, who's going to tell us a little bit about dark energy. So take it away, Paul.
Okay, thanks for having me. I appreciate it. Yeah, we're going to be talking about dark energy and how dark energy may change everything about the way we think about everything from fundamental physics to cosmology and beyond. When dark energy was first discovered, or at least announced, in 1998 as existing due to the observations of redshifts of distant supernova, many in the astrophysical community viewed it as an important change, but in some sense, a minor change or a minor variation on the Big Bang model that already existed. Today, we call this the lambda CDM model, lambda standing for dark energy or cosmological constant, and CDM standing for cold dark matter. So it was basically a change from what had been the CDM model to now the lambda CDM model. It made everything fit better, that all the observations that existed before, but it didn't really change the general story of the Big Bang model, namely that the universe was once hot and dense and has been expanding and cooling to the state that we observe it today. On the other hand, as I'll try to argue today, dark energy is much more than that. It's potentially something that changes everything, the way we think about everything. So if we ask, what is the current consensus about the universe? Well, it depends on whom you speak to, but here's a common consensus that one hears. One, that string theory is the only self-consistent theory of fundamental physics, that string theory has an energy landscape that we'll talk about in some detail, that string theory naturally incorporates inflation, lending strength to inflation, the inflationary theory. That string theory also, one of its supposed successes is that it explains the solution to the cosmological constant problem. That inflation is the only way to explain the universe. There's no other valid or reasonable idea. There's a whole world of theorists who work on effective field theory these days and think it's a valid approach for cosmology as well. Most would say that dark matter is either a WIMP or an axion, some form of dark matter of that sort, some sort of weakly interacting particle, and that dark energy is best fit by a cosmological constant. And when I say that dark energy changes everything, I mean dark energy potentially forces us to reconsider all of these claims. Let's begin with the string theory side of the story. So, well, just a little historical fact for some of you that don't know. I was in Princeton during the time that the announcement of the supernova measurements were made in 1998 that showed that their universe was undergoing a period of cosmic acceleration, and that suggested, or strongly suggested, there was some form of dark energy which occupied 70% or more of the energy density of the universe. For those, when I would go to seminars at that time in Princeton, the astrophysicists were very accepting of this notion. And part of the reason why they were accepting of it is because some of us had even been claiming there was already strong evidence, at least statistically as strong evidence for cosmic acceleration and dark energy, or at least for dark energy, prior to the announcement of the supernova. So when the supernova results came in, for some of us, this was really a confirmation of already something we strongly expected had to be true, and sort of completed the picture, sort of finished the picture. If there was any uncertainty, it was how the supernova results would come out, and they came out consistent. On the other hand, if you went to those seminars, you would discover that the string theorists in the room were very frustrated. And the reason why they were frustrated is because dark energy, or in particular cosmological constant, was very difficult to incorporate in theories of superstring theory, partly because of the supersymmetry and partly for other aspects of string theory. In fact, it seemed that the only possible vacuum densities one could get in string theory were either 0 or negative. And here the data was telling us that we were living in a universe in which the vacuum density was positive. And this created a lot of concern. And so often the string theorists would be very aggressive in attacking the speaker who was presenting the supernova data, challenging them on all sorts of grounds, whereas the astrophysicists were more accepting. And this frustration continued to grow over the next few years. And what finally broke the ice was a paper, this paper by Katru, Kalash, Linde, and Trivedi, KKLT paper in 2003, which claimed a solution to this problem of incorporating dark energy, a positive vacuum density, into string theory. What they claimed was that if you include all kinds of contributions that one can have to the energy in string theory, that one obtained in the end a very complex energy landscape. That instead of just getting vacuum minima with 0 or negative energy density, if one included a number of complications into the extra dimensions, D-branes, fluxes, non-perturbative effects, etc., you could lift those minima, which were negative, to be positive. The solution, in order to get a solution which was positive, one had to use all these different ingredients, which could fit in various ways to sum up to lift these minima from positive to negative. The solution was kind of a plumbing or a plumber's solution. That is to say, it had many parts that had to fit together in different ways. And because it was a plumbing solution, one didn't have just a single vacuum emerging from this construction. One had many of them. And by many, I mean, well, by first estimates, 10 to the 500, and those estimates have gone up over time, but just some incredibly, unimaginably big number of vacua with different lifts, different constructions with different amounts of lifting that would produce valleys in an energy landscape like an alpine landscape with mountains and valleys, and where these valleys, these vacua where physics would be stable, locally stable, these vacua, depending upon the details of the construction, could have all kinds of heights. In fact, could have all kinds of physical properties. They could have different masses, different couplings, and other physical properties. And the claim was that because this landscape was so vast, somewhere in this landscape, there had to exist one just by chance, even just because there were so many of them, that would have the right value of the positive cosmological constant. And hopefully the right particle physics as well, right fundamental physics as well. It was also claimed that when you have these mountains, some of them are sharp and steep, like in this diagram. Some of them would not be so sharp and steep. Some of them might even be flat enough to support inflation. Okay, but now you had a problem. Okay, you have this energy landscape. We would, in this picture, correspond to one of these vacua minima. How do you manage to get that vacuum, that particular valley occupied versus the others? And the only solution that they had in mind was that, in fact, you end up ultimately occupying all of them. That inflation, once it starts, if indeed you can support inflation, once it starts, it's going to start due to quantum fluctuations. There's a quantum runaway effect that's well known. It leads to eternal inflation, which leads to a multiverse. Now, normally we talk about a multiverse. We talk about in cosmology a multiverse in which the universe is broken up into patches. It's mostly inflating, but there are patches which it's not inflating, which have every conceivable cosmic possibility. Some are flat, an infinite number are flat, an infinite number are not flat, an infinite number of closed, an infinite number open, an infinite number have different microwave backgrounds than what we observe, etc. And now what KKLT were proposing is there's a second kind of nearly infinite multiplicity, is there's 10 to the 500 different possible values which you could lie in, and the multiverse would also produce patches which occupy each and every one of those. Therefore, the properties that we observe in our universe are simply an accident of which particular quantum fluctuations led to the end of inflation in our region with its particular properties, which happen to be flat and uniform when they didn't have to be, and now would also have different physical properties, different masses, different couplings, different forces, etc. So you were left in a situation where trying to incorporate dark energy into fundamental physics, you were basically forced to an outlook in which you could never really explain the universe in its entirety, because we only see a piece of one valley, a piece of space that belongs to one particular valley. And there's nothing fundamental about the particular properties we observe. They could have had completely different properties if we lived in a different valley, or ever so slightly different possibilities if we lived in yet other valleys. There's nothing fundamental about anything we observe. It's also, therefore, nothing particularly predictive about this outlook, since anything that we happen to be observed is an accident. It has no deep cause. And this idea, and if you hear this idea, just if you hear the idea of the multiverse and you hear the idea of the string landscape, some of us, I'll certainly put myself in that number, would be extremely frustrated because really this is a theory which is quite different from normal science, which has to have which by construction, for ordinary science, it must have the possibility that there's some measurements or combinations of measurements that could falsify the idea, at least in principle. Whereas in this kind of picture, whether it's a cosmological measurement in the multiverse or a fundamental physics measurement in the landscape, there is no such thing, since anything that can happen is likely to happen someplace in the multiverse with the string landscape, with this alpine-like string landscape. And so the argument back was, well, tough luck. That may have been your vision, that you wanted to make science predictive and have scientific theories be falsifiable. But since string theory must be true, okay? Since it must be true and it leads to a string landscape, we have no choice. This must be the way we go in fundamental physics. But there's one problem that came along with this idea. That was 2003. In their papers, they presented an argument for why this string landscape must exist. They presented these complex constructions, but they didn't complete the constructions. They didn't quite make that clear. Well, I guess if you read the paper carefully, it is clear, it's there in print, but they didn't emphasize it enough when over the next years they strongly promoted this idea of the alpine landscape. They didn't make it clear that they actually had not completed any of these constructions. That is to say, they left out some parts, some contributions to the energy, which they couldn't compute, assuming that it would just do the job required, complete the lifting of the minima. In the meantime, well, let's say, here's 2020. There's supposed to be 10 to the 500 or 10 to the 5,000 or 10 to the 100,000 minima or more. You might ask, okay, they've had 17 years in which to complete these constructions. How many complete constructions do there presently exist? How many vacua do we actually know exist? As to say no exist, as to say we can do a mathematical calculation that's self-consistent and complete and shows that they exist. Not necessarily one that exists that corresponds to our observed universe, but just any one of these minima, even the simplest one you can choose. You can choose any one. And the answer in 2020 is that the net number is exactly 0. not one is currently constructed. And the fact that it was hard, that when you went out to try to complete the constructions, you found it difficult to do, led to a different viewpoint. I know you heard last week from Hiroshi Oguri, and I imagine he talked about something about along the same lines, but I'm going to continue this discussion anyway, not knowing exactly what he said. So what evolved in the string community as a result of this frustration that one could not actually construct anything, any of these vacua at all, was the development of a different theory of string theory, a different outlook on string theory, which took account of this problem that one couldn't actually construct these vacua. And this is what was termed, this was first introduced by Kunrun Vafa in a very simplistic form in 2005, and has sort of come back in the last few years to get a lot more attention as it's become further developed. And the basic notion is that if you look at the energy landscape, it's not the alpine landscape that had been claimed by KKLT. All those vacua which are supposed to live well above sea level, that is to say, with different possible positive cosmological constants, are actually underwater in the true picture of string theory, was the claim. Underwater means they had a negative, or some of them might have a zero cosmological constant, but there weren't all these minima with positive cosmological constants. So a very different outlook. And furthermore, there were certain constraints. If one ever was going to try to describe the universe in string theory, not only could we not live in one of these valleys because they correspond to negative cosmological constant, whereas observations tell us that we have a positive dark energy density, but furthermore, any theory that is going to be consistent with string theory and more generally with quantum gravity had to obey certain conditions, certain constraints. The first of these constraints is, I've called here the range conjecture, is often called the range conjecture. And this has to do with the scalar fields in your theory, the scalar fields that might describe inflation, the scalar fields that might describe the Higgs, the scalar fields that might describe the dark energy density. And the range conjecture said that if you want to have a consistent theory of quantum gravity, you have to make sure that the range that your field traverses over time is bounded by an amount I've called here delta, which is of order 1 in Planck units, in reduced Planck units. If there are any, yes, let me just say that. And by the range, you have to include the fact that if you're, for example, in the example of the Lagrangian I've shown you here, there's a field space metric, Gij, capital Gij, you have to include that metric in your measure of range. So having several fields, each traveling a little distance, doesn't really help if the net distance traveled in field space exceeds 1 in reduced Planck units. What would happen if you traveled more than that range is that new degrees of freedom would appear in your theory that would destroy the validity of your effective field theory. In fact, the general view here is that effective field theory really doesn't work in the context of quantum gravity. There are many perfectly legitimate effective field theories as judged by self-consistency and in the way that we judge effective field theories that will be impossible and incompatible with string theory and quantum gravity generally. So for example, the theories that would describe any one of those minima with positive cosmological constant are perfectly good effective field theories, but they're not theories that can be incorporated in a valid formulation of quantum gravity or string theory. That was the Swampland conjecture or the Swampland claim, which was opposite that of the landscape claim. The other constraint, which came more recently, is is what's called the slope conjecture, and then there are various variations on the slope conjecture. And this is a very important one we'll see. This one said that if you calculate the slope of your potential, or more precisely, the field gradient of the potential over the potential itself, and if you are thinking about a potential which is positive, which you might have in a valley, or that you might have anywhere in the alpine landscape, then everywhere the slope must have the property that it's greater than some value which is of order 1. That means if the potential is positive, well, let's see, before I say that, there are refined versions of this conjecture. By refined, I mean the conjecture has been enhanced a bit to include known cases that do look like they're consistent with quantum gravity. So there's a slight refinement which says that either the slope has to be greater than a certain value, or the curvature has to be negative and below a certain value. One of those two conditions must be obeyed.
Hi, can I ask a question?
Yes.
So this equation that you just wrote, it is clearly perturbative enough a prime, right? Would you say that those two conjectures, they are holding for perturbative string theory, or they should hold all the way up to the string scale?
So the claim is in the Swampland reasoning or conjecture, this is true generally, non-perturbatively as well. In fact, what's happening as you exceed those constraints is that you're getting huge back reaction effects that are invalidating your effective field theory.
Okay.
So even though it would look perfectly good, for example, let's look at the second one, it would look perfectly good as an effective field theory. It wouldn't be, you would necessarily generate degrees of freedom that would invalidate your theory.
Okay, thanks.
Now, I just want to emphasize that if this slope conjecture excludes any local or global minimum with V greater than 0. So in particular, it eliminates the possibility of any kind of metastable or stable cosmological constant. So it's not a small deal, it's a very big deal. Now, what were the arguments? I explained the arguments for the landscape. They were based on a calculation which was not complete, and which was simply assumed that there would be additional contributions that would complete the lifting of the minima. What were these conjectures? What was the Swampland picture based on? It was based on, well, what Kumumvafa likes to tell me is evidence. I always find that a bit funny because evidence to me means an experiment, whereas he was actually talking about theory, that the attempts to actually make fully consistent, controlled constructions in string theory had shown that these conditions are generic to all the examples known. And at least up to this morning, when I looked on the net, there's no counterexample. So we have these 2 points of view, which are competing with one another, okay? The alpine landscape picture of string theory, which says that everything is possible, nothing is excluded, and therefore, in some sense, there's no point in doing a test because anything you would find would likely be possible somewhere in this landscape. And the string swampland landscape, I'm calling it alpine and swampland, the string swampland landscape, in which at least a few things are excluded, the range constraint and the slope constraint among them. Now, curiously enough, even though it's just a few things and everything else is you're allowed to imagine anything else, that's enough to take you from a theory which has no testability to no falsifiability to one which can be falsified. So suddenly, string theory is on the line. There are tests one can perform in principle that can check whether or not it's consistent with what we observe about the real universe. So suddenly, dark energy moves to the fore as the key thing, the key element, because that's what's forcing the whole thing, as the key element, our key way of testing the whole structure of string theory that's been developed over the last decades. Let's see what its implications are. I mentioned in the outset that one of the things that many people in the community believe is that inflation must have occurred. It's essential to explain the universe that we observe. But now we can ask the question, is it consistent with the swampland? And if the swampland describes string theory or quantum gravity generally, because the argument really goes beyond string theory to say that any theory of quantum gravity must obey these conditions, is inflation compatible with that? Well, let's check. The range constraint on scalar fields is violated by essentially all inflationary models you've ever heard of, and by at least a factor of 5 to 10 during the last 60 folds of inflation. I don't know how many of you have ever played with trying to incorporate or build models of inflation from scalar fields, but if you've done that, you know what I'm talking about. That in order to have 60 folds of inflation, we need a field range which extends beyond a Planck length by, as I said, factor of 5 to 10 or more, depending upon the details during the last 60 e-folds. So this is already a contradiction, a mild contradiction, but a contradiction with the swampland constraints. But it's a very conservative statement I made here, because it's 5 to 10, it violates the range constraint by a factor of 5 to 10 if you have exactly 60 e-folds. Now, who's to say, with 60 e-folds I'm using as the minimum number you need to explain the smoothness and flatness of the universe. But this is very conservative, because if you think about inflation being driven by some scalar field rolling down a potential, the 60 e-fold mark corresponds to some particular point on that potential. And what we're saying is we need the field to start exactly there, no higher, to get this 5 to 10. If we assume that it begins, since there's no particular reason why it had to be exactly 60, no reason why it couldn't be 70, 100, 1,000, 100,000. All those things are possible in models that people build every day in inflation. And then violate the field constraint, the range constraint by more and more, depending upon your model. So actually you violate, unless you make the very odd assumption that there were exactly 60 e-folds for some reason that we have no reason to expect. Unless you make that argument, you should realize you're actually violating this constraint by quite a bit in practice. But even more worrisome is the slope constraint, the slope conjecture. All single field inflation models and most multi-field inflation models significantly violate the slope conjecture. If you translate the slope conjecture, the constraint on the slope of the potential over its value, in the case of a field slowly rolling down a hill, then you find that it's directly related to the equation of state that you have during inflation. So I'm calling the equation of state here epsilon, as you see on the left. And the equation of state, epsilon, is equal to 3/2 1 plus W. Some of you may be more familiar with W. W is the ratio of the pressure to the energy density. So epsilon and W are sort of equivalent ways of describing the equation of, parameterizing the equation of state. And epsilon is equal to 1/2 of what? Of grad V over V, the very quantity we've just constrained according to the slope conjecture to be greater than of order 1. And if it's greater than of order 1, then the slope conjecture boils down to the constraint that epsilon is greater than of order 1/2. Now, in inflation, epsilon also determines the number of e-folds of inflation, what I'm calling n sub e. And exactly what the relation is depends a little bit on your model, the form of your potential. Most of the simple potentials that one thinks of in inflation, power law forms and the like, are potentials in which the power alpha there is 1. So if alpha is equal to 1 and epsilon, according to the slope conjecture, has to be greater than 1/2, then this is completely ruled out. This is completely inconsistent with all those models. None of those models can be embedded into valid models within the context of string theory or within the context of quantum gravity generally, according to this picture. Because those models require a very small value of epsilon to be consistent with the data. In particular, the measurement of the constraint on the tensor fluctuations, or B mode, which produce the tensor fluctuations, which produce the B mode polarization patterns in the cosmic microwave background. The constraint that due to the fact that we don't yet see those B modes already tells us that epsilon has to be quite small. If you go to models with greater values than alpha, so I should say, in the cosmological community, the result of the constraint on B modes that we have today has essentially wiped out all the textbook models one had of inflation. Look up any book on inflation and say, what are the models they consider to be simple? They're all in this alpha equals 1 class. The fact that the B mode data has given a strong constraint that rules out this class has led the community to do what? Well, to add new parameters and to tune things. And that essentially is one way, essentially amounts to pushing us to a new class, which corresponds to alpha equals 2. But to make those models work and to satisfy the B mode's constraint, you need even smaller values of epsilon. Even more inconsistent with the slope conjecture. So the way we're being pushed by the data when it comes to inflation is pushing us into deeper and deeper conflict by many orders, by increasing numbers of order, by an increasing number of orders of magnitude with the slope conjecture. And this too is very conservative, because I'm only talking about the conditions on the potential or the conditions on epsilon during the last 60 e-folds. If you think about most inflationary potentials, almost all of them have the property, if you follow them far enough away from those 60 e-folds inflation. For example, consider a plateau potential, which is one of the popular examples that still passes the B mode test. That has a plateau that gets flatter and flatter as you go along the potential. That means V prime over V, or equivalently, the equation of state, epsilon, is going to 0, ever closer. That even more strongly violates this constraint. So both by the range constraint and by many orders of magnitude, the slope conjecture, one has to conclude that inflation and the swampland are in very serious tension. And by very serious tension, I mean, forget it, it's in trouble, that they're not consistent. Which means all those claims that string theory naturally gives you inflation are inconsistent with this swampland picture. Okay, that we're inconsistent with the swampland picture. I'm sorry, the inflation is inconsistent with the swampland picture because it requires a very flat, if not absolutely flat, potential. Another example where that occurs is in the case of dark energy. Now, a big difference between the story for dark energy and inflation is that, first of all, whereas for inflation, we don't just need a potential which is flat, we need it to be flat for at least and to maintain it for a duration of at least 60 e-folds. That means the universe has to grow by at least into the 60 during the time that the field occupies this flat region of the potential. For the case of dark energy, as far as we know, dark energy has only been observable or measurable component of the universe for about maybe 1 or 2 e-folds. And so the constraints on the potential are much weaker. Similarly, the constraints on the equation of state are much weaker. In the case of inflation, the absence of B modes puts a very tight constraint on epsilon, forcing you to tune like crazy in order to satisfy the B mode constraints. We don't have the same constraints on dark energy. So the story for dark energy is qualitatively different, or maybe I should say quantitatively different, in terms of satisfying these constraints than it is for inflation. Let's see how they apply, though. The slope constraint, first of all, does have one immediate profound effect, which we already mentioned. It does mean that we can't have the dark energy cannot be due to a cosmological constant. It rules out the possibility that the vacuum density of the universe is positive, whether it be metastable or stable, because whether a metastable or stable, V prime would have to be 0, and that violates the slope constraint. If, on the other hand, we observe that the universe is cosmically accelerating, and we're told that we can't have a cosmological constant, what else can we do? Well, the other possibility is to have some sort of time-varying dark energy density. A dark energy density which could be described by a field rolling down a potential in which the gradient is non-zero. It satisfies the slope constraint. On the other hand, it's rolling slowly enough that it produces an equation of state which is much less than 1, which is the condition you need for cosmic acceleration. And this idea has actually been around for a long time, since actually there's already beginning to develop before the supernova measurements. I mentioned earlier in the introduction that when the supernova measurements were first revealed in I think it was January 1998, it was not such a surprise to the astrophysics community because there already existed a chain of evidence, a strong chain of evidence. In fact, quantitatively, I mean, measured in terms of sigmas, it was a stronger chain of evidence that already suggested that we lived in a low density universe with a non-zero cosmological constant. I give at the bottom of this transparency a reference to the paper by Jerry Ostreicher and myself in 1995, which appeared in Nature, which made exactly that claim, that there was overwhelming evidence already for a positive cosmological constant. It's an interesting historical fact that that paper was not well accepted at the time because it used a technique that at the time was not considered, that was novel, and that made some astrophysicists uncomfortable. Instead of relying on just a single measurement, what we did is we combined a combination of different measurements to see where they overlapped in terms of what they told us about the matter density and the amount of dark energy density. And when you asked what region, whether there was any region of parameter space that was consistent with all existing measurements, it turned out to be a rather narrow region, which everywhere in it had a dark energy density or cosmological constant that was at least 70% of the total energy density of the universe, which curiously enough is consistent with what we observe today from more precise measurements. It wasn't accepted at the time because this idea of putting together different measurements with different systematic errors on a single plot at that time was unfamiliar to people, although today it's what we do in all our cosmological measurements. So when the supernova measurements came around, as I said, it was not a surprise. It was more like, good, that's one other piece of data that fits this same restricted region of parameter space. In the meantime, some of us were already thinking about the idea that the dark energy may not be a cosmological constant. It might be some sort of time varying, might be due to an energy component with some sort of general equation of state that's even time varying and different from that of a cosmological constant. And we call this quintessence. And so the idea of quintessence has actually been around all this time. And now it comes back to the fore in the context of the Swampland argument, because it's the only hope, according to the Swampland conjecture, of making theories of quantum gravity or string theory that are consistent with what we observe to be true about the universe. It's namely the fact that the universe is accelerating today. Okay, but we also come with a constraint. which is this epsilon, must be not too small, just as a case for inflation. It must be, say, of order a half in order to be consistent, because if the grad V over V is of order 1, then epsilon is of order a half. Is that consistent with observations? And that's what we first examined in this paper with Kumrun, student George Obier, and Pratik Agrawal a few years ago. And here's what we found. Step 1, you might first consider the case with a constant grad V over V. That's what an exponential potential gives you. The grad, remember, is a gradient in the field gradient. So it gives you a constant grad V over V. So if the potential is e to the lambda phi, then grad V over V is just lambda. So what you see in the plot on the left is, first of all, a bunch of colored curves. These are the predictions for the change in the equation of state W. Now I'm going to use W, pressure over energy density, as a function of redshift versus redshift. So if I take one of these exponential potentials and roll the field down, okay, instead of getting a constant W or a constant epsilon, I get a W which is changing with time. And you can see the trend is always, as you roll, over time, the field is picking up speed, which means as you go from large redshift equal to 1 on the right, to redshift 0, the present on the left, the general trend of the curves is they all curve upwards. So the kinetic energy of the field is growing compared to the potential. That means the pressure is growing compared to the energy density. That tends to make W grow as you get later and later in time. The solid line, black line, is the constraints from the data. So usually, so if you've been looking at all the constraints from the data on equation of state or dark energy density, it's often expressed as a constraint on W, today, the value of W itself, rather than a value of W as a function of Z. When people are doing that, they are assuming that they're taking the data and they're using it to constrain models in which W is equal to a constant. But there's nothing to say that W has to be a constant. So if you're going to start considering models, or general models as we want to now, in which W may be changing with time, you have to do a completely new analysis relative to the observational data. And in order to extract not the constraints of W, but the constraints of W at different redshifts. And you see that when you do that, and I think that was first done, I think this was the first paper to do that actually, as one of its side results, you see when you do that, what you might expect, which is as you go to larger redshifts, where you're running out of supernova, begin at redshift 1, the data is less constraining on W. If you come to very small redshifts, when you also get a very little constraint, because again, if you get too close, you're running out of supernova. So the constraint really comes over a certain range of redshift. If you ask what the data really is constraining, it's really putting its tightest constraint on a certain range of redshifts, mostly around redshifts between 0.2 and 0.4, or if you could say 0.35 if you want to be more precise. That's where its tightest constraint comes from. And if you want to make a model that's consistent with the data, you must make sure that its prediction for W of Z fits below that black curve at its most sensitive point. Because this curve is already several sigma. And if you violate, let's say like the models which are correspond to lambda equals 1 or 0.8, or even the 0.71, you're already violating the observations by the best observations by several sigma. So what we conclude from this is that we can manage to slip under the constraints, do the limbo and sort of slip under the bar and slip under the constraints, but only if lambda is small enough. And by small enough, 0.6, 0.65 or so. And in terms of epsilon, lambda is directly related to epsilon because it's related to the grad V over V, and 1/2 grad V over V squared is epsilon. That gives us a constraint on epsilon, and it tells that epsilon has to be less than 0.18. And that's already a problem because remember the Swampland constraint was demanding that epsilon be greater than 1/2. So there's already a tension. Now, you might say, okay, when the Swampland conjecture was posed, it didn't really give a stiff bound. It gave a soft bound, order 1. So maybe this is not yet an absolute no-go for string theory. But it does tell you, curiously enough, that we are already in the game of testing string theory or testing quantum, our current understanding of quantum gravity, because we're already sensitive enough to be putting pressure on the value of epsilon that it constrains. You might also say, but hold it, you chose a very special potential. Why didn't you choose one with a more general form in which lambda changed as a more general function of time? Well, I won't go into the argument here, but if you look into our paper, what we show is this is actually the best you can do for any potential. The best you can do is the constant lambda case. If you make lambda a function of time, it only pushes epsilon further towards 0 when you look at the constraints on epsilon even further towards 0. So this is the best you can do, and it's already in tension. So is it compatible with observations? Well, you might say, it's a little scary. Let's be generous and say yes, but barely so. And future observations may make matters worse, or future observations may reveal that epsilon is of order 1/2 or 0.18 or something like that, in which case it not only proves that dark energy is a form of quintessence, but it fits rather nicely in this picture. So one of the consequences that I'm saying is that future experiments on dark energy are now very, very interesting.
Hey, Paul, it may be a point in time to mention the H0 connection here. Hello?
You mean you mean the H0 problem and the question of the current seeming conflict between what we might call cosmic measurements and local measurements?
Yeah, so basically it seems like in generic quintessence models, H0 gets pushed lower than lambda.
Yeah, so in general relativity, so we're assuming Einstein general relativity at late times. Seems like a very solid assumption. It's consistent with everything we know. If you look at the second Friedmann equation, it tells you that h dot over h squared is equal to minus epsilon. So that tells you that h dot is always going to be decreasing with time if you're consistent with Einstein gravity. Cosmological constant corresponds to epsilon equals 0. So the best you can do is have h dot equals constant, h dot equals 0, therefore h equals constant, I meant. Okay, then when you add quintessence, that corresponds to a positive epsilon. And since h dot over h squared is equal to negative epsilon, that means h has to be sloping downwards. So if you're going to introduce any form of quintessence with Einstein gravity, it only makes the matters worse in terms of it does not help cannot help resolve the H0 problem. It just makes H decreasing more rapidly. If you want to solve the H0 problem, well, it's another subject of discussion, but if you think the H0 problem needs to be solved, and that's not clear to me, but if you think the H0 problem needs to be solved in the sense of a new model of fundamental physics, you have to do something much more dramatic, probably to change gravity, even at low energies where we think we understand it well, or to introduce some form of null energy condition violating form of stress energy or some combination of the two.
So just to say, Paul, that I think string theory is getting pushed in that direction, right? Towards something exotic.
Yes, and even more so. That is actually the bottom line of where we're heading.
Good, thanks.
Yeah. You could also talk about the future of the universe. The future fate of the universe is that the field is it's one of two possibilities, two possible fates. One, the field keeps rolling downhill, the potential remains positive until the range constraint is violated. Once that happens, new particles will begin to appear spontaneously out of the vacuum and essentially occupy the entire universe, and the universe will end in this rain of new particles that are produced with a kind of whimperish end. The other logical, and you can estimate how long that will take, given the slope and range constraint. And I won't go into the details of the calculation, except to say you get a number of order 10 or so 10 to 100 eFols, which is to say, given that the present age of the universe is 14 billion years, we're talking about factors of 10 or 100 times that. Something dramatic has to happen to the universe in terms of its particle content in tens to hundreds of billions of years, maybe a trillion years. The other possibility is the slope does not change, it goes negative. It simply go downhill and go negative. And if that happens, what will happen is that the accelerated expansion of the universe will stop first, because as the potential disappears, that's what drives the accelerated expansion. That's going to go to zero. That's going to disappear first. The next thing will happen as you continue to go downhill is that actually the expansion of the universe will stop. So we've gone from accelerated to decelerated. The expansion of the universe will stop, and then the universe will reverse to contraction. So that's another kind of possible fate to the universe. But either way, there's some kind of future fate to the universe which makes it dramatically different from our current universe. Either way, it's the end of the world as we know it. Now, among these two possibilities, it's curious that the second fate fits very beautifully in a completely different idea that I'm not talking about today, which is the idea of bouncing in cyclic cosmology. If you're going to have a cyclic universe, the universe can't remain in the same state that it is in today. It must be that the acceleration stops and reverses to contraction. And the way that it actually is constructed in most cyclic models is precisely in the way we're being forced in this picture, to introduce a form of quintessence as the source of dark energy, which drives a field downhill, down a potential, which becomes negative. That's exactly what we introduce in the case of cyclic cosmology. So I'm not going to make a big deal of it in this context. It's just to point out that one shouldn't throw away this idea just because it wasn't what you expected in terms of what people had previously viewed as standard Big Bang inflationary cosmology. Maybe that idea, for various reasons, isn't right. Maybe there's an alternative idea, and this alternative idea happens to fit beautifully with what you're being pointed at. But one thing you might ask is, why should you take the swampland seriously, given that only we're dealing with the evidence that we have by Kuhmann's evidence, namely, we've looked at lots and lots of possible vacua states in string theory, and they've all turned out to have zero or negative cosmological constant, or to have a potential which slopes down the way we've done it. After all, there are 10 to the 500 or more of these vacua, and certainly Kuhmann and his team and collaborators have, and all the community that have been nowadays working on swampland, haven't explored all of them. Okay, so maybe it's just waiting around the corner to find the one that does fit. Well, I'm going to give you a reason why I think it's a deeper problem than suggested by the evidence. And this comes from a completely different line of reasoning that I and collaborators have been involved in as well, which analyzes a more general class of models, which is simply compactified models with compact extra dimensions generally, whether they come from string theory or they don't come from string theory. So there's a tradition to this line of reasoning as well. It goes back to the 1980s, Gary Gibbons in the 80s, and numerous authors listed below the see also line, which considered in the context of cosmological constant. But the papers at the top that I'm referring to consider this line of reasoning in the context of general cosmic acceleration or general quintessence. So it's more it covers a much wider range of possibilities. The nice thing about this line of reasoning is that although it's a closely related framework, because many string theories, in fact, essentially all the string theories that we think about that are supposed to be phenomenologically plausible fit within this framework, okay? So it's, here we're only using the fact that there are compact extra dimensions and that we have some higher dimensional theory and lower, which is described by Einstein gravity, which combines to a lower dimensional theory, a 3+1 dimensional theory, which is described by Einstein gravity. It doesn't involve conjectures. Once I tell you that I begin with a theory, a higher dimensional theory that obeys Einstein gravity and compactifies to one, a lower dimensional that obeys Einstein gravity, then it's purely a calculation that one does to ask, is it consistent with cosmic acceleration? And if so, what kinds of cosmic acceleration? So there's no conjectures, it's just calculation. It's also more general. We don't assume anything about a scalar field and a potential. We're simply talking about the equation of state. And the moment I tell you you're accelerating, I'm telling you something about the equation of state, no matter what might have been the cause of that acceleration. So that's what's nice about this complementary line of reasoning. And it also gives us insights at what the source of the problem might be when one tries to build models or construct models in string theory. It's a little bit blind when one does the string theory calculation. You try to put together the calculation. It's not quite clear why things are failing. It might be, in the cases of interest, it's failing for this reason. So the line of reasoning goes something like this. As I said, we're going to assume we're considering a general class of theories, which is as compactified extra dimensions. I don't care too much about how many extra dimensions, so I'll just call that capital D. It could be the 6 of string theory or the 11, or sorry, the 7 of M theory, whatever you like. We're just assuming that they both obey Einstein gravity. We do assume a form for the metric for this calculation, at least for the one I'm presenting here, and that it's what we call Ricci flat or conformally Ricci flat. This is the form of metric that is assumed in almost every string theoretic construction that are actually all the ones I know at present, which are also supposed to be phenomenologically plausible. So you have your usual dimensions described by x and t in the first term, okay, multiplied by a conformal factor. And then you have your extra dimensions y described by the rest of the metric, and they separate in the way that's shown. One can consider more general metrics, but the proofs are quite straightforward for the examples that I'm showing here. And then we further assume that null energy condition is satisfied. So those are the conditions we're asking, and we're asking, is that consistent with dark energy? Do we need to violate one or more of these assumptions? Well, I'm going to try to very quickly run through this because we're running out of time, just give you a gist of how the argument goes. So we're asking, we said we're insisting that the null energy condition be satisfied. What does the null energy condition mean? It simply means if you contract the stress energy with null vectors for any combination of null vectors n, that it has to be greater than or equal to 0. It has nothing to do with energy being 0. It has to do with this condition. The terminology is a bit annoying. Now, this has to be satisfied at every space-time point if we're going to satisfy the null energy condition. If it's satisfied at every space-time point, then it's also satisfied if I compute what I'll call the A average null energy condition violation. What I mean is essentially the expression I'm writing below. If I integrate the expression on top over the extra dimensions, y, with some weight factor, which I just called e to the a lambda. And so then a to the 8 omega, I'm sorry, e to the a omega. Okay, omega can be a function of space and time. If this particular combination is violated for any particular a, then the NEC, the null energy condition, also has to be violated. In other words, if the integral with some weight, some positive weight is 0, then surely somewhere in space-time, Tmn and m and n must also be 0. So this is kind of a crude test of the null energy condition. Crude by that I mean, if you get a negative value, you violated the null energy condition. If you don't get a negative value, that doesn't prove anything because you did an integral. And it could be you had some places where it's negative and the integrand is negative and some places where it's positive, such that the integral is positive. So you can't conclude anything if you get a positive value. But it turns out this is good enough to produce a powerful test and a simple test. And for simplicity, although what I've really given you is a continuum of tests, because I can choose A to have any value I want, and I can choose my function omega to have any function of space-time I want. It's really a continuum of tests. I'm going to keep things simple. I'm going to just consider the case of A equals 2. Now, if we have extra dimensions, which I'll call the total number of extra dimensions is K, then the metric along those extra dimensions can be broken up into a trace component, whose coefficient tells you the size of the extra dimensions, and a shear component, which we'll be less interested in, sigma mn. If I change the sizes of the extra dimensions, I'm effectively changing the Newton's constant. So what I call zeta 2 over here, which is an integral over that trace part, is a measure of how much the Newton's constant is changing in time compared to the Hubble constant. Now I take the Einstein equations, and I can, assuming a general form of energy density with pressure P in the 3 dimensions, and P sub 3 in 3 dimensions, and pressure P sub K in the extra dimensions, and energy density rho, I can reformulate the Einstein equations in the way shown here, where I'm again averaging the Einstein equations. Now, I should say, so on the left of these equations, I've organized, and the top one represents, so the top one, I should say, represents the average version of the Einstein equation for the 3 plus 1 dimensions. The second equation represents the averaged for the uncompactified dimensions. We want to try to satisfy both sets of Einstein equations at the same time. If you want a consistent theory, they both must be satisfied. You can already guess that the reason why I wrote the equations in this way is that on the left-hand side, I have this combination of rho plus p's, rho plus p3 or rho plus pk, which are the measure of whether or not we're violating the null energy condition. If they're 0 or positive, we're satisfying. If they're negative, then we're violating. We want to ask, are we forced to violate the null energy condition? If either of those averages turns out to be negative, it turns out that's enough to prove that you have to have violated the null energy condition somewhere in your theory. So now I specialize for the case of A equals 2, and I've rewritten the 2 equations in a slightly simpler form. I've left off a lot of the details because I just want to point out the simple structure of them. Let's look at the first one. The first one I can write on the right-hand side in terms of what we observe, the actual energy density of the 4D effective theory times epsilon, the equation of state. The second term involves the time variation of G, because one degree of freedom we can play with is have the extra dimensions expand or contract, okay? And then the third stuff is a bunch of those other terms, which you can show are all negative semi-definite. Which means, if we look at the second term, we notice that it's negative. And the third term is also negative. So just looking at this equation at all, we can make a surprising conclusion. Let's consider the case that of a cosmological constant. If the universe has a cosmological constant, that corresponds, and it's truly a cosmological constant, that corresponds to W equal to -1. If you make W equal to -1, you notice that the first term is now 0. The second term has to be 0 or negative, and the third term is 0 or negative. So if we have a cosmological constant, we have a problem, because the thing on the left hand has to be negative. And if the thing has to be negative, then you violated the null energy condition. So this argument already is telling us having a cosmological constant is problematic in such theories. But it's much stronger than that.
Sorry, Paul.
Look at the second.
Sorry,
yeah.
A quick comment. So this is assuming extra dimensions. If we got rid of the extra dimensions, we would find that lambda saturates the null energy condition, right?
Correct.
So this is all coming from...
Yes, this is specifically a problem of having any kind of compactified theory.
Good, thanks.
Yeah, and I'll make that point stronger. I'll come back to it in a second, Owen. Okay, now let's look at the second line. The second line is actually worse than the first line, because in the first line, for a cosmological constant, the worst case is we got 0 for the first term. Now we have a term when we make a cosmological constant which is negative. Okay, so it's greater than 0 for cosmic deceleration, epsilon greater than 1. But for any form of cosmic acceleration, this term is negative. And the more you get close to a cosmological constant, that is to say epsilon equals 0, it's getting more and more negative. And it's proportional to the energy density. So it's not a small contribution, it's big. Then there's a second term. Then there's a bunch of terms on the right which are less than or equal to 0. And then what's our only hope? What's our only hope for saving this equation so that it gives us satisfies the null energy condition? The only hope is that middle term. The only hope for not violating the null energy condition is to have G dot be changing with time. But that's kind of tricky, because if you introduce a time-varying Newton's constant in order to save this equation, in order to make it net positive, then you run into trouble with the first equation where we had a negative G dot over G squared. You see, they kind of push against one another. What is all this numerology telling us? What it's telling us is that compactified theories have a problem with cosmic acceleration. That if you try to have cosmic acceleration, they have a back reaction on the extra dimensions, which it wants to force them to expand. If you don't, if you don't violate the null energy condition, it wants to force them to expand or contract. That's causing G to change. I believe that's the fundamental problem one's really up against, going back to string theory and the swampland. That if you have any kind of extra dimensional degrees of freedom, cosmic acceleration in the compactified theory has a back reaction on the extra dimensions that is forcing them to change. Can you satisfy observational constraints when having G change with time? Well, actually, when I first began working on this 10 years ago, there actually was a small range in which you could be consistent with the then existing constraints on G dot over G, and also satisfy those two equations without violating the null energy condition. But in a recent paper, we showed that with improved constraints on G dot over G, in fact, they've improved remarkably. I haven't actually seen that emphasized in many places, but they improved by several orders of magnitude. If you improve them in this way, actually nothing is left. I'm going a little bit, I won't go over the details of this graph, but the conclusion is that actually it's entirely excluded. There is no model that's consistent with the constraints on G dot over G that can also balance those equations. So the conclusion is that it's incompatible with cosmic acceleration. Something has to give. Yes, as you suggested, Owen, one can give up entirely on the idea of extra dimensions. Okay, but that's a pretty dramatic thing, and that's a pretty dramatic conclusion, and many people would resist that conclusion because it's been seemed like such a powerful idea, going back to Kaluza-Klein, Einstein, and string theory, and the like. It seems to be an idea that it's also that helps us solve problems in quantum gravity. So you wouldn't want to necessarily give that up easily. The other possibility is you give up on null energy condition being satisfied. And that's also a dramatic thing because the example, although it's not impossible to violate the null energy condition, what we've also shown in this paper is this null energy condition, it's more than it has to be violated. It has to be able to change with time in a very specific way as the universe goes from decelerating to accelerating at around a redshift of 1 or so. And it's very hard to invent or imagine such a form of null energy violation that would do that. In fact, we have not succeeded in finding any reasonable example at all. Doesn't mean it's impossible, I'm just saying it's highly and tightly constrained. Curiously, though, this violation of the null energy condition has been what for some in the community has been one of the roadblocks for thinking about bouncing in cyclic cosmology. Because in order to bounce, or in order to have cycles, you have to go through a period in which the universe not only goes from expansion to contraction. That's easy. A field just rolling down our quintessence potential can do that. But if you want to cycle, you have to go back from, or bounce, you have to go from contraction back to expansion. And that requires either violation of the null energy condition or modifications of gravity. So the idea that one might have to modify gravity in a more fundamental way or violate the null energy condition is exactly what was called for in order to make cyclic cosmology or bouncing cosmology work. As again, it's a different subject of discussion, but it's kind of interesting that the two ideas meld together nicely. So in some sense, what I've argued is that dark energy could be the end of the world as we've known it. All these ideas that we thought were fundamental, that string theory has an energy landscape, that string theory naturally incorporates inflation, inflation's a good thing, it's the only way to solve the universe, that string theory also explains the cosmological constant, that it's okay to use effective field theories and approach as a valid approach in cosmology, that the dark energy is a cosmological constant, all those things go out the window, and there's even some issues with the dark matter sector, which I didn't discuss. So that's the bad news. Happier thoughts is that a new world may be emerging, which also leads to exciting new directions for theory. It suggests new directions to turn to accommodate dark energy within quantum gravity. Something's going to have to give, what's it going to be, and whatever it's going to be, its consequences. It's a brand new frontier. It also suggests, I didn't discuss it, a novel relationship, possible novel relationship between dark energy and dark matter. So it gets us to not only rethink dark energy, but also dark matter. And it suggests, it's through an completely independent line of argument, suggesting that we need certain new ingredients, maybe null energy condition violation, or at high energies, deviations from different deviations from Einstein gravity. These also support or are consistent with new theories of the origin, evolution, and future of the universe. So at the same time that certain ideas that have been around for many decades may be on the wane, it's providing a window or a frontier for new directions. So I think I'll stop there and ask for questions.
Okay, thank you very much. I think Paul Frampton has a question. Paul?
Yes.
Question?
Oh.
Hello. Can I ask a question?
Yeah, you ask it first, yeah.
Yeah. Yeah, I have a basic question. So regarding the Swampland conjecture, is there some intuitive understanding why string theory allowed that Swampland?
Why string theory, for which one, the range constraint or the slope constraint?
Yeah, both.
Well, there is, so as originally conceived, the way I presented it, it was based, as I said, on the evidence, okay? Just based on what the experience was and actually trying to do these constructions suggested by KKLT and finding how they failed, finding failure. But since the work I've been talking about, there's been another line of reasoning which supports the Swampland conjectures. And this is based on a different conjecture. It's a different line of reasoning, a different conjecture called the Trans-Planckian censorship conjecture. And what that conjecture says is that, it starts from scratch and says, okay, you can do whatever you want in cosmology, except you can never have a situation in which fluctuations which are on sub-Planckian scales when you start end up on scales in which they become classical, in which they become on scales in which they ever obtain wavelengths larger than the Hubble radius. Now, this is exactly what happens during accelerated expansion. During accelerated expansion, the scale factor is growing exponentially, and quantum fluctuations on small scales are being stretched to large scales. And if you have too much acceleration, they'll eventually accelerate to the point that, as I say, more than 60 folds of inflation, they'll eventually accelerate to the point that they will exceed the Hubble scale. And you should look at, you can look at the paper. That's another line of papers, again led by Kumun Vafa and different collaborators. By that constraint, you end up with essentially this only a slight modification of the constraints which I presented to you. So they essentially derive that, and they think that derive those the Swampland conjectures I've described to you simply from the claim that you can't have sub-Planckian fluctuations ever grow to be classicalized by this to say growing bigger than the Hubble radius. This also is telling you that you can't have a lot of accelerated expansion. It doesn't say it has to be zero, but it has to be, it's rather tightly constrained. It again is inconsistent with inflation, which needs more than 60-folds of inflation. It's slightly more accommodating for dark energy, but not enough to make a difference for the not to change the answers that I've given you today.
Okay, thank you.
But you might take a look at that. It's a different line of reasoning.
Oh, okay, thank you.
We have 2 more questions online. Paul Frampton.
I'm not hearing you.
Paul has a question.
Oh, you're muted, Paul.
But I have to unmute. Can you hear me now?
Yes, I can.
So I have a couple of questions. When you discuss the way the Swampland conjecture leads to, and the future of the universe, you mentioned that it leads to a possibility of turning around the expansion into a contraction, as in a
Yes.
cyclic universe. What about, does it also give some idea of insight into the bounce when the contraction turns back into an expansion?
Not directly, no. It can fit within models of bounces that exist in the literature. So we do have examples, at least in the literature, which seem to be stable bounces, classical bounces. But so it's consistent with it, but it doesn't. You're too far away from the bounce to force that condition.
Mm-hmm. And a different question. On your last slide, you say something about a novel relation between dark matter and dark energy. Can you amplify on that?
I'll say a few words about that. So if you have a form of quintessence, any kind of quintessence models, one of the things you always have to worry about is quantum corrections that couple that field to other degrees of freedom. So for example, if it couples to any ordinary matter degrees of freedom, it's going to change masses and couplings. And usually in a way that, for example, for what we're talking about, for the kind of epsilons we're talking about, usually in a way which will violate empirical constraints that currently exist. So you have to find some way to protect that field from having such interactions. In the context of string theory, the easiest way to do that is to have it correspond to a moduli field that's controlling some part of the extra dimensions, which does not include the ordinary sector. A sector where some sort of what we'll call dark energy controlling the size and extra dimension of a dark sector. A natural place to put dark matter is in that dark sector, which means that if you're following, this is where it's a suggestion that if you put those ideas together, if you say, okay, I have to have a dark sector to explain dark matter, I also have to have a dark sector to protect my field, why not make them the same dark sector? And in which case, dark matter and dark energy are linked in that energy can be transferred from one to the other. And one example of that is what's called the fading dark matter idea, which is that as this field is rolling along, it's changing the mass. It's also continuously changing the mass of dark matter particles that exist in this decoupled dark sector. So that's an idea that was inspired by this reasoning. Could have been there before, but it was inspired by this reasoning. And it might be the best way to accommodate things, I don't know. But it's an interesting idea that deserves its own independent evaluation.
Does it give any idea what the mass of the dark matter constituent could be?
No, because when you put dark matter in the dark sector, that's up in the air. Not only does it not tell you the mass, it doesn't tell you whether it's self-interacting or if it's WIMP-like or what it is. So you have for better or worse, you have a lot more freedom to have whatever property, to design whatever properties you want.
Okay, thank you.
So when you push things in dark matter into that sector, the nice thing about a WIMP, it's in a detectable sector. You've now pushed the dark matter into a sector where it only, as far as the ordinary matter is concerned, has gravitational effects, although they could be these complicated effects between dark matter and dark energy, which might be interesting. I should say, because Owen had asked the question about the H0 problem, one of the things that this does is affect H0 measurement, because essentially you're draining energy from dark matter and putting it into dark energy as you go along. And although it doesn't change what I said about the Einstein equations, it does produce a kind of bend in the redshift luminosity curve, which mildly alleviates the H0 tension. Okay, it doesn't solve it, but goes in the right direction. It's a kind of tricky thing. But so if you're interested in that, I would look at the papers. There's a nice paper on fading dark matter. That's what it refers to. Fading in the sense that it's losing its mass.
And who are we?
That's
Okay.
again Vafa and OBA. I don't know, is it OBA? I don't remember the authors. Sorry, I don't have that in front of me.
Paper, right?
But Vafa is one of them.
Yeah.
Oh, sorry, you said, Owen, you said something?
Yeah, so Pratik is on that paper, right? So he's your collaborator on the 18.
I thought so. Yeah, okay. Yeah, I was
With George's.
trying to reconstruct it in my mind live, and I didn't quite. Yes, Pratik Agrawal would be another author on that paper.
So I think we, Paul, if you're finished, we have one more question from Shipi.
Okay.
Well, I have a final question. Is there anything in the dark matter discussion which would disfavor dark matter constituents with many solar masses?
Not in what I was well. That's outside the realm of what I was talking about, because these were fundamental particles. So now you're talking about how they organize and clump. That's a different issue. So I think it's agnostic about that.
Okay, thank you.
Oh, and you were gonna, yeah. Nice to see you, Paul.
Good to see you. Yeah.
Okay. We have one more question, right? Shivi?
Yes.
Hello, can you hear?
Yes. Hi.
I have two questions. The first one is that it seems that this strain landscape based on the KKLT is not consistent with the Swampland conjecture. So can you comment on how we understand this? I mean, what is the problem of this KKLT uplift to the strain landscape?
Yes, okay, yeah, I should have said a little bit more about what the landscapers would say, because it's not like they've given up. Okay, so if you look at their paper and you read carefully, or you even read their recent papers, they will point out that there's part of the calculation which they cannot do, which are the non-perturbative corrections. And they would argue that although we can't calculate them, surely they'll come in all forms, including ones of the right sign that will be enough to lift from negative to positive values. But they're incalculable. Then incalculable, and we don't have the techniques for calculating them. So that would be that is their hope, that someday we learn to calculate them and show that they are good enough to solve the job. And that would be the theory, the version of string theory that describe our universe. However, I'd like to make a comment about that, which is, okay, everything we believe on about string theory being good for explaining low energy physics is based on the idea of extra dimensions and perturbative calculation. Now you're going to come and tell me to explain the vacuum, you're going to have large non-perturbative calculations. Why should I believe that those non-perturbative calculations are only going to affect the vacuum density and not affect everything else? And so why do we believe, it puts a question about everything in string theory, not just the vacuum density. So maybe, I think one should keep an open mind, but that's the challenge, which no one at this point knows how to tackle. Now, Vafa would give more general arguments. Vafa would give more general arguments why he thinks that's not going to save the day, that's inconsistent with quantum gravity. But they're, again, conjectures, so you can look at those.
Okay, thank you. The second question is that do you believe in the future we can try to polish this constant C and make it more precise and compare with the experiment? Theoretically, can we narrow down the constant C?
The constant C for the slope, you mean? The epsilon, or is that what you
Yeah.
meant? Yes.
Yeah,
I
the
mean,
C is
yes,
slope one.
it's a long haul. Yeah, I mean, astrophysical experiments, which are designed to improve our measurements of the equation of state of dark matter, will slowly and gradually push down the limits on epsilon, or detect it, or detect a time variation. It won't be, to get another order of magnitude in the next decade or so is about what, optimistically, the most one could expect. But
Yeah, but I mean,
in
in string theory, in theoretically, can we make some kind of a lower bound for C? Something like that.
Could you get a
Because
lower
you say
bound?
order one, but yeah.
Oh, yes. So in this, what I mentioned before, this trans-Planckian line of argument, there is a stiffer lower bound that's obtained. And it's around 0.7 in what I call lambda. So it's marginally inconsistent with the current data. So they get in that line of argument, there is a stiffer bound because you have a limit to how much acceleration you can have. That means it must cut off after a certain amount. And that's enough to tell you, give you a constraint on this epsilon, a theoretical constraint on this epsilon. And so it's better than the order one estimate.
Okay.
In our
Thank you
case,
very much.
in our argument, any amount of acceleration is a problem. Yeah.
Thank you.
Thank you.
Any more questions or comments? It appears, actually, Paul, can I ask you about this Ricci-Flat condition?
Okay.
Conformal Ricci. So how much of a limitation is this conformally Ricci-Flat or Einstein gravity? 2 and 3 you never addressed, right?
Oh, if you give up on Einstein gravity, I mean, if you relax,
Like
either of those. So Einstein gravity is a big thing to give up. Okay, that means you're going away from the paradigm, right, of compactified theories, and then anything goes. If you're allowed to do anything you want. So obviously that one is, including violate the null energy condition, but you don't even have to do that. You can find other means of satisfying the conditions, but you have to. So that's a big one to give up. Ricci-Flat and conformally Ricci-Flat. The reason why those are introduced is because they're easy to do the calculations and because they do describe all the phenomenologically accepted theories at present. I've been looking at alternatives, and the problem with alternatives is that not only are they ugly, but it's really hard to see how you're going to we don't have any scheme for recovering good particle phenomenology. So how should I put it? It's discouraging to follow that direction.
So essentially,
in other words, I would be looking for cases where I first know I at least have a chance of getting reasonable particle phenomenology, and then testing. And I don't know any example at present. I've been asking around, but I don't know any such examples.
So this wouldn't hold for SU3 structure manifolds, maybe for SU3 holonomy, right? For Calabi-Yau type things.
A lot of these arguments would carry forward for that case as well. The details would be different, but there'd be a constraint.
Okay, thank you. I think
there's even in the literature someplace, but I have to look for it.
Okay. Well, thank you. So it seems more questions or comments, so we can thank you for an extremely interesting talk.
Okay. Well, thank you all for your patience. I'm glad we were at least able to meet remotely.
Okay. Well, have a good day, Paul. Okay.
Same to you.
Take care. All the best.
Same to you. Thank you.
Thank you.
Bye-bye.